right. And then we'll go ahead and double check. Make sure it's recording. Yep, looks okay to me. I'll just come back and check it again, maybe after 5 minutes or so, just to make sure it doesn't run out of buffer space again. I don't think that's the actual issue. All right, so back to the homework assignment. So to answer your question, I'm going to do this without GDB. How's that? Okay. So we'll go ahead and start with the same file. Oh, I downloaded it once already. So we'll go ahead and decompress that into today's folder. Extract. And now that it is extracted, I just go to that folder using any terminal would work. So CD 2012-0209. Go to mem1. It actually puts in the parentheses too. Let me change the file name, the folder name to mem1. What is going on here? What are those backslashes doing here? They are escape characters. A backspace is an escape character in a Unix type environment. In other words, if I want to type a name of a folder that itself has a space inside, I cannot just say mem1 space something, because the space is also used to separate parameters on the same command line. So in order to make sure that the command line or bash understands that the space is actually a part of the file name and it is not a separator to separate different components on the command line, I use the backslash symbol to say that, oh, I'm escaping the next character. Do not let bash interpret that space character. It is a part of the name of the file. That's what the backslash is for. And the same thing applies to the parentheses, because parentheses also have special meanings in bash. And then I can just rename it to mem1. So this is the original file name. I give it a new file name, mem1, and that renamed the folder. You can also use a GUI to do the same thing, but if in case anyone wants to use the command line to do this, this is how it is done when you have funny characters inside a file name or folder name. All right, so let's go to the folder and we'll go ahead and do the homework assignment, but without using GDB in this case. All right. Now, if you cannot use GDB, you can still use, like a piece of paper to help you, so that you can show the content of the bytes. Now, I'm not going to use a piece of paper. I'll just go ahead and do this in line so that I can display the actual content of the memory. The first one is 123. It is 123 in decimal. I have to convert it into hexadecimal. Binary is good, but hexadecimal is even better because it's much more concise. So I want to do everything in hexadecimal in this case. You are allowed to bring your calculator into the test. So your TI-89, 81, just about the entire 80 series has base conversion. Are there any questions, or does anyone want to confirm whether the TI-80 series calculators have a base conversion? Yep. Do they all?
Like my TI-86 does, but
so it doesn't have base conversion?
No, it does.
It does? Okay.
I think we can treat this.
Yeah, I think all calculators now, have a base conversion. Even if you pick up a $5 one at Staples, most of the time those have base conversion too. Unfortunately, I don't have a calculator here. Now, since I don't have a calculator here, I will have to use either GDB or some other way to do the base conversion. Let me see.
I have it on a piece of paper.
You have it. I'm trying to figure out, how I can do this, so that you can do the same thing in a test.
Okay.
Okay. 123 in hexadecimal.
So the print command only works in GDB to convert it. You won't do it directly from the terminal.
Say again?
The print command won't do it directly from the terminal. It has to be in GDB.
Right, because GDB is the one that that is actually doing all the work. It's not Bash, or the command line interface that's doing all the work. Now, Bash may have something similar to that, but I'm not 100% sure. But in this case, it's actually pretty easy. I can do this by hand. because 128 is 80 in hexadecimal because it is 8 times 16. So in this case, this number is 5 less than that. So it's, it's 80 in hexadecimal minus 5, which turns out to be, is it 8b? 7b. Oh, 7b. All right. So the first one is 7b in hexadecimal. The second one is 23 in hexadecimal to begin with. And then the next one is an octal number. If it's an octal number, you kind of have to convert it into base 2 first, and then from base 2, convert it back into base 16. So as an octal number, the 1 is 001, the 2 is 010, and the 3 is 011. Then you break it up into 4-bit chunks from the right-hand side. Remember, you have to do it from the right-hand side and not from the left-hand side. So now we end up with 2 nibbles. Each nibble can be represented by a hexadecimal digit. 101 is 5, so this is hexadecimal 5, and the other one is just 3. Okay, is that okay? I mean, does everybody kind of follows the base conversion process? Then we have L1, and then on this line we have the ASCII codes of 1, 2, and 3. The ASCII code of 1 is in hexadecimal 21, and then the other one is 2, 2, and then the other one is 2, 3.
Is it 3, 1?
Is it 3, 1?
3, 1.
Oh, okay. Otherwise the homework cannot be done. And then we have the dot longs. Now the dot longs are the ones that you have to be extra careful about, because up to this point everything is byte wide. Okay, every single construct takes up exactly 1 byte, and the i386 is byte addressable. So there's really no issue about, is it a big endian processor or is it a little endian processor? But when we come to dot long or dot int, actually it's the same as dot int, then we have to think about how we want to deal with this. We already know that in octal, 0, 1, 2, 3 is in hexadecimal 5, 3. But this time I'm using up 4 bytes to represent exactly the same value. So if you want to list everything by bytes, then you would have the least significant byte occupying the lowest address first, and then we have the padding zeros, the more significant digits, taking up the higher bytes. So these 4 bytes will represent 0, 1, 2, 3 as a dot int or dot long. They're basically the same thing. And the next one is 0, 1, 2, 3 in hexadecimal. So that means the least significant byte, which is hexadecimal 2, 3, will be at the lowest location. The next one will be the second least significant byte, which is 0, 1 in hexadecimal. And then we have the most significant bytes, which are all zeros. Any questions about this part? No questions about why the 0x23 and the 0x01 are kind of flipped? It's all because it is little endian. The least significant byte is stored at a lower address. The next one is 123 in decimal, but we already have figured out that that really is just hexadecimal 7b, so we'll say it is 7b and then the rest are zeros, because once again we store the least significant byte first. Okay, so without using calculators, I can at least get this part done. Now this is a different story. You can kind of do it, without a calculator. I'll show you how to do it without a calculator with base conversion. It can still be done. It's just a little bit harder to do it this way. So I'll open up another terminal, or just use another terminal here to do this calculation. Okay, copy, paste. Okay. So as long as you have a calculator that can do division and subtraction, you will be fine. So I have a really primitive calculator here. It's a command line calculator. There's a command line everything in Linux. Okay, so we start with this number. How do you convert this to a base 16 number? It would be nice if I have a mod operator, which I'm not sure whether it has it or not. Nope, that's definitely not mod. Let me see if I have a bitwise AND. No, doesn't have that either. All right, fine, we'll do it the difficult way. We divide it by 16. Okay. What am I seeing here? That's the result of the division. But obviously, this is not a base 16 number. It's not even close to a base 16 number. So how do we look at the division, the result of the division, and then figure out what is the least significant byte or the least significant digit in base 16? The least significant digit of the base 16 number is going to be the fractional part, which is 0.0625 times 16. That is the remainder of the division. If I were to make this division, separate it into the quotient and the remainder, in this case, the remainder is 1. Okay? So on the other side here, I will just basically write down the hex version of 545253 is, okay, we know the last digit or the least significant digit in base 16 is 1. Now it's time to move on to this part of the number. Divide it by 16 and basically do the same thing again. So we'll go ahead and divide this number by 16. And then we take the fractional part and multiply that by 16. That is a 3, which means the remainder of that division is a 3. So we know the second least significant digit in hexadecimal is a 3. And then we'll do the same thing. You can tell that this is really quite boring once you know how to do it. So we'll go ahead and copy and paste this, divide it by 16 again, and that's another 3 because it's the same number as the previous time. So we have another 3 here. And then we take this number here, which is the quotient of the previous division, divided by 16 again. And then this time we have, another 3. And then this time we take the 83. Now 83 is relatively easy to convert because 83 in decimal is 5 times 16 plus 3. So I know right away this is just 53 in hexadecimal. But if you're not sure about that conversion, you can do the same process, just do it one more time, and then you have the 53 in hexadecimal. So switching back to here, I have another 5 and another 3, and now we have the hexadecimal representation of the decimal number that was kind of big. Now, you have to remember that you don't really have to do this too many times because a number up to 4 billion in decimal only requires 8 hexadecimal digits to represent. So that means in the worst case, if I give you a 32-bit number, in the worst case, you only have to perform divide by 16 8 times. That's the worst case. Is that sinking in? Okay. So now we have a hexadecimal number, and we can separate it into 3 chunks, or to be better yet, to separate it into 4 chunks, because we want to look at it in the byte by byte thing. But this is organized as now because this is a source of confusion. This is a base 16 representation of the value that I gave you as a decimal number. But that's not how it is organized in memory. When you list bytes out in memory, you have to remember the left-hand side is the one that has the least address. So when I want to figure out the organization, then it should be 031, the least significant byte should be listed first, and then the 33, and then the 53, and then the 00. So now I have a complete layout of how memory is organized here, and also I know what I'm looking for in EAX. Because this is what I want to get, this is what I want to copy into EAX in the end, and this is how it is organized in memory. Are we doing okay so far with the process of doing the homework assignment? Okay. So we take a look at this whole sequence here, or I should be saying, I should be looking at these 2 bytes particularly, because I want these 2 to be the most significant bytes of the register. Is it EAX?
Yeah.
Well, it's 132-bit register. The point is, there's no specific way to only address these 2 bytes. Okay, if you want to change the most significant 16 bits of a 32-bit register, you have to use the move long instruction and change all 32 bits. So that is this is the constraint that you can use to help you quickly locate which part of memory should I use in the first instruction, in the first move instruction. So you look at the initialized portion of memory, which has, okay, let me just rewrite this part here so it's easier to read. Because the first line represents the base conversion, so I want to do a second line to actually look, list out the content of memory. Okay. All right. So we have. This is how memory is organized. I have two places where a 5.3 is there. Okay, because I want a 5.3 in the most significant 16-bit of EAX. So that means I have to copy from somewhere that also has a 5.3. Here's one 5.3, and here's another 5.3. I gotta choose one to copy. So which one should I choose? Well, let's take a look here. If I want this particular 16-bit number to be in the most significant 16-bit of register EAX, I need the memory to be organized like this because of the little endian organization. So that rules out the first one, because the first one has a 5.3, and then the byte that is following that is a 3.1. The second one has a 5.3 to begin with, and it has a 0.0 as the second byte, which matches exactly how we want memory to be organized down here. Is that okay? But a move long instruction cannot just move 2 bytes to the most significant part of the register EAX. It has to move 4 bytes. So that means when I want to move these 2 bytes into the most significant part of the register, I'll be moving 2 additional bytes. The question is, am I moving these 2 additional bytes, or am I moving these 2 additional bytes?
Top 2.
It'll be the second option. It'll be the second option because I want to move these 2 as the most significant 2 bytes, and the least significant 2 bytes will just have to go along with the ride, so to speak. And as less significant bytes, they will have a lower address than the bytes that we were just looking at. So that means we'll be copying these 4 bytes into register EAX in order for EAX to end with to have 5.3 and 0.0 as the most significant 2 bytes. Is that doing okay so far? But the beginning of the copying is here. So now we have to figure out what is the address of this portion here. Well, this is L1. L1 is defined to be the address of the first byte of the 1, 2, 3 as a string. In other words, L1 is the address of this byte here. This is L1 plus 1. So that's why we need to use L1 plus 1 as our first instruction, or the address of our first instruction. So I'll just put it here, move L, L1 plus 1, and move it into register EAX. But we are not done yet, because once we do this, then we'll be copying these 2 bytes into the least significant bytes, and these 2 bytes into the most significant bytes. It takes care of 3 of the 4 bytes that we have to copy. The byte that is still wrong is the least significant byte. EAX is going to have 3.2 as the least significant byte instead of 3.1 according to our calculation. But that's okay because you are allowed to use 2 instructions. So now it is time to use a second instruction to patch things up a little bit. Now this is also where you have to understand how a register is organized. EAX, AX, AX, and AL, they are different windows to look into the same 32-bit register. So that means sometimes you can just look at a register from the window of AL and therefore only change the least significant byte of EAX as a 32-bit register. So now we have to find a 3.1 to copy from. Well, out of this entire thing, there's only one byte 3.1, which is this byte here. The address of this byte is just L1 itself. Okay, so we need a second move instruction, but this time we have to be very careful because we don't want to move any more than a byte. If we move more than a byte, it will also clobber the other byte which is already correct. So we have to use a move byte instruction going from location L1 at address L1 and move it into AL, which is the least significant byte of EAX. So that should accomplish what we have to do in this homework assignment. Yep.
What was the purpose of the byte? 'Cause, if there was, let's say, you need to access the memory up there, how would you do that? Because there wasn't any label.
Well, if there are no labels like L1, I can still survive because I can still use _start.
You can also just do L1 minus 1.
No, I think okay, what was his question? If there's no L1, right? If there's no label.
He wonders why you put the byte up there, but probably just to make the homework more of a challenge, just a little bit. He didn't want to give it to you too easy.
Exactly. This homework assignment can also be done even without this label completely, because _start is also a label in the same section. So that's why you can always count backwards in this case and say _ minus something, and _start minus something. Yep.
So in the second line, I use move
In which
B,
line?
On the move BL1 to AL.
Uh-huh.
I just move B
Uh-huh.
and then to EAX. Is that the same thing, right?
Say again?
I just move BL1 and then move directly into EAX. Is
The
that
assembler will complain
plan?
because if this is a move B instruction, you cannot specify EAX as a destination.
Just give you a warning.
It will give you a warning.
But is that going to be fine? Is that still fine?
It depends on what you call fine is.
Is that still
It is
like
fine as in it will still generate the right opcode. It is not fine because you really should fix all the warnings. So in terms of the behavior of the program, yes, it will behave correctly. But in terms of whether you want to do this when you're at the job, writing your program, no, it is not fine. Okay.
So if we're talking about the homework, is that still okay?
I have not decided yet. But since I did not specifically say you have to get rid of all the warnings, maybe I'll just let you slip this time. How about this? I just verbally say from now on, you guys will have to fix all the warnings.
Oh, thanks.
It just makes sense, because it doesn't even matter whether you're in an assembly language programming class or C++ or Perl or Java class. If the tool is giving you a warning message, you really should fix it. Because a lot of times the warning message means something. Most of the time it is telling you that I think you might have made a mistake. That's what the compiler is saying. Syntactically speaking, this is correct. But in terms of the context, something is not connecting. So that's why it is always a good idea to turn on every single warning that the compiler can turn on, and start with that. There are other ways, other tools that can let the compiler, let the tool find out more potential problems. And the more you can rely on the tool to give you the warnings and potential problems, the better, because you can catch problems earlier instead of later in those cases. Yep.
I got a question. Does AL register, does it mean that it will move this extra one at the beginning, and if it was like AH, it would move to the end?
AL is a window into the least significant byte of EAX. So it will only change bit 0 to bit 7 of a 32-bit register EAX.
I think your question is it's not the end, it's the very next one after AL, right? Is that correct? He's wondering where AH goes. AL, then AH, and then the rest.
Yeah, it's AL is bit 0 to bit 7, AH is bit 8 to bit 15, but the rest of a 32-bit register has no particular name. Yep, go ahead.
I've got a question about the little endian convention. So the way that the bytes are arranged in L1 in memory is that the least significant digit is the highest, and I'm wondering if the little endian convention is being applied a second time on the register and it's reversing it again because of the endianness, or is it not, and that's why it's going the opposite way?
Okay, the endianness only applies when you have to deal with memory locations. A 32-bit register is a 32-bit register, so there's no quote-unquote such thing as endianness when you're only talking about a register. However, when you are moving or when you're copying 4 bytes from memory into a register, then you have to pay attention to the endianness, because now the question is the first byte in memory copied to the most significant byte of the register, or is it copied to the least significant byte of the register? So am I?
memory then that has, it's only in memory that it's little endian, and then when it goes back to the register, it goes back to what you'd expect it to.
Correct. Only when you're dealing with something that is inherently byte addressable, then you have to deal with the endianness. You know, whether it's little endian or big endian, you still have to figure out which one is which one. But when you're dealing with registers, for instance, if you copy EAX to EBX, then the endianness is a non-issue, because you're copying 32 bits as one chunk into another 32-bit container, so there's no need to worry about which byte is going where. There was another question. Go ahead.
So line 17, it says this is organized as 31335300. But we don't really care that it's organized that way because it's going into the register the other way, right?
You kind of care because this is exactly how you want these 3 bytes to appear in memory in this particular order. And we found that here we have 33, 53, and 00. So it is significant from that perspective. Is how do I find this particular
But
bit pattern
00
in memory?
goes in. It would be like the most significant in the register. 00,
Correct.
53, 33.
Yeah, but something still has to go there. I mean, this this byte is the byte that goes into here in the register. So you still have to find it and make sure it is 00 instead of something else. Okay. Any other questions? Yep.
I had it's related to this, but not to the program. So what if we're using a program like Power, right? And there's 2 programmers that are writing to EAX, what would happen? Is they gonna wait till the next program runs, or?
Can you ask the question again?
So what if we're using like a terminal, like for instance, the school has Power, right?
Okay.
And both of us are trying to write to the register EAX.
Okay, both of you being two
You're
different
running
users.
the programs. Yeah, 2 users.
Well, every time you run the program, it starts up a different process. Now, in this class, we don't really talk about the concept of a process. How many people know what is a class versus an object in C++ programming? Just simple object-oriented programming concepts. A program, like the executable file that we look at on on the disk, that's like a class. In other words, it's just sitting there. It's not using any memory resources on the computer. Okay. When you run a program, when you run the program either by GDB or when you run the program just by its name on the command line, it's like instantiating or creating an object out of a class. So if you run the program once, on your own terminal, that creates a process. It's like an object. If somebody else, even if you, open up another terminal and run the same program again, that's a different process. In other words, you use the same program, the same class, but to create 2 different objects. And the 2 different objects are not related to each other than they come from the same class. So there should be no interference whatsoever.
So what if, like, at one point the user wants to retrieve EAX? Will he get something that the other person wrote
No,
in?
there's no way, because each object has its own properties and its own attributes and its own, everything. Yep.
But it doesn't. You're right that they won't modify each other.
Right.
But they all still point the same. EAX is still the same with both of them. But they push and copy EAX and then process or
Yes.
switching processes.
The kernel keeps track of all that stuff. It will save
Still
and
one
restore the
EAX.
registers.
Yeah, that's
not
what I was
multiple per
wondering.
Oh, I see. So
That's
your
exactly.
question is seen not from the perspective of the debugger, but from the processor's perspective.
Well, we only know that there's one EAX, so I'm just wondering at what point in time will be in there. So
Okay.
But
So to answer your question, you have to remember this analogy. So more analogies. There's only one processor. Okay. Now, for the purpose of our discussion, we don't even have to consider multi-core processors, because this concept works on a single core processor without even hyper-threading. There's only one register EAX in hardware. When you run your program and somebody else has run exactly the same program, or all programs try to access EAX for various purposes. So the question is, how can the system run all these programs and not have EAX all messed up? The answer is this: timeshare. Okay, just imagine the processor is a condo, okay, in Tahoe. Okay, you are one process, you are one process, you are one process, you are one process. So when it is your turn to use the condo, you move in with everything that you have, okay? But when it's time for another process to run, then you move everything out and put it into a U-Haul storage place. And then you move in with everything that you have. Okay? So there's still only one kitchen sink, there's only one washer, there's one dryer, and so on and so forth. It's just that when you leave the condo, or when you're evicted sometimes from the condo, you also have to move everything with you. Is that working out okay? So from your perspective, you have your own register, you have your own stuff in the condo, but in reality, your stuff, quote unquote your stuff, is actually only in the condo when the process has, the processor actually running your code. When the kernel decides, hey, you have been using the processor for way too long, it's time to evict you, then the processor, the kernel, will actually arrange the movers to move everything that you have in the condo into a storage.
Where does it actually go?
And put you into suspend mode, so you'll be hibernating, and you won't even notice the passage of time in that case. Yep, go ahead.
No, got it.
Okay. But that's a good question. It's a little bit beyond the scope of this class, and thank you for clarifying his question, because I thought he was asking from the perspective of the debugger, which is only looking at the process itself, but he's actually asking from the perspective of the processor. Very good. Good questions. Any other questions? No other questions? Now, since you asked that question, I'm going to digress just a little bit. Just a little bit.
There was one time when data.
No, this time it's actually a little bit better. No, I don't want to read my mail. Actually, I got everything on some profs now, so I can actually go to some profs for that. So if you go to some profs and say ~t audion, it goes to my own stuff, okay, which is not in Moodle. This stuff, you don't have to log into Moodle to access it. So you can go to, this is really old, by the way. I mean, most of this stuff is like ancient. You go to develops, and then you can go to real-time kernel. Now, what a real-time kernel is a miniature operating system. It does not have a file system. It doesn't store files or anything like that, but it does support multiple, threads of a program executing at the same time. Okay, so from the question that you're asking, you're basically curious about stuff that is going on inside a kernel of some kind. And this is a tiny little kernel. It doesn't do a lot of stuff that a real operating system does, but it does have multi-threading, which basically ends up with the same question. Okay, now that I have all these different threads basically running quote unquote at the same time, what is happening to the resources of all these threads? Each thread, seems to be able to make calls, function calls, deal with return values and stuff on its own. So how does that happen? So this stuff this is way beyond the scope of this class, but I'm just saying that you might find this interesting. If you have spare time, you might want to read some of this stuff here to answer some of those questions that you were asking. Those were basically questions you should ask in a upper division class at a 4-year university operating system class. That's what they talk about in those classes. All right. But I like those questions. Okay, so are there any questions about this homework assignment? It's all good? Let's go take a look at the second homework assignment. Mem 2, you have 1 week to work on this one, the second homework assignment, and you look at this and go like, tag, you just copied and pasted, didn't you? And the answer is, yes, I did. And replace Mem 1 with Mem 2. All right, but the link is new, okay? This is called mem2.tar.gz. The organization is about the same as the other one. You have one file, which is your homework assignment. So let me extract this, to a folder, so that we can just, take a look at that. Okay, right click, or just extract to today's folder, which is this one. Extract, and then we can switch back to my editor. All right, this is your program. This is your second program. And you can also see that it looks kind of similar in some ways to the first homework assignment, but it's definitely not exactly the same. You probably want to start with reading the instruction itself. I want register CX, which is a 16-bit register, or better described as a 16-bit window into the 32-bit register that we call EAX. I want CX to have a value of 400 in hexadecimal. I don't call it 400 because 400 implies it's a decimal value. I call it 600 in hexadecimal at this point, which is this point here on line 17. In other words, before the next label, which is after, I want CX to have a value of 400 in hexadecimal. This result must be guaranteed regardless of where the operating system chooses to load the program. In other words, the program can be loaded, high or low. I mean, depending on the distro. I have seen, a different distribution. Ubuntu and Debian tend to use the same mechanism, so they end up at the same place. But I have seen someone on the notebook computer that loads the program to like a completely different address. So don't rely on the program being loaded to exactly the same address every single time. You are allowed only to fill the blanks as indicated by the underscores, and I'll point out where the underscores are. No new instructions or directives are allowed. You cannot add anything, you cannot remove anything, you cannot even change the addressing modes of the operands. Okay, so you do have a small degree of freedom, but not as much as in the previous assignment. In other words, you are free to specify what goes here, but you cannot change it to become a non-immediate operand. This has to be an immediate operand. You can specify what goes here, but you cannot change it to a register operand. You cannot change it to be a immediate operand. This has to be a direct operand. If it doesn't start with a % symbol, if it does not start with a $ symbol, and there are no parentheses in it, then it has to be a direct operand. Okay? And there's one more place you can also play with. It is this place here. This place specifies an offset to a based scaled indexed operand. And you can specify just the displacement / offset of that particular operand. And the end result is I want 400 in register CX after these instructions. So another big Easter egg hunt. This one is a little bit smaller because if you just look at how I initialize memory here, you already know where I'm going to get the 400 in hexadecimal. The question is, how do I use these instructions with all the restrictions that I have mentioned to get to those 2 bytes, the 0400 bytes.
So the ECX, or the CX is actually the 16-bit part of the ECX. Yeah.
Yes, but I don't care what is in the most significant part of ECX. I only focus on the least significant 16 bits of ECX. Okay, so here's your new homework assignment, and it has one thing that we haven't seen before, but you should probably know what it means. This is kind of new, and that's kind of new too. I use .int just like I use .int in all the other places, except in this case the expression is not a constant. It refers to a label, and I do some calculations with a label too. So then the question is, what exactly does it do?
Is it okay that it's defined before the label? It's defined before.
Oh yeah, it's fine. To the assembler, there's no such thing as you have to define a label before it is used. So it can be defined before or after. Okay. So the first thing you want to do with this program is to find out exactly what the .int on line 3 is doing, and also what the .int of line 6 is really doing. I suggest you use the X command to examine memory locations. Look at those 4 bytes as a single 32-bit number, but display it in hexadecimal. And then you can compare that to the label L1 itself, and then you can get some clue of how to proceed with this particular assignment. But that would be the very important first step, is to understand what line 3 is doing and also what line 6 is doing. Okay. Well, just to give you a hint before you start with this homework assignment, what exactly is L1? It's a label. Okay. And what is the purpose of a label in an assembly language program?
Address of the first byte.
A label has a symbolic name that makes it very, very easy for us to refer to it. And it is always going to resolve to a number of some kind. Okay? In this case, L1 is defined. Which line defines L1? Does not refer to it, but instead defines the label L1. Line 5. Okay? Line 5 defines the label L1. And what is it defined as in this case?
A bookmark at the beginning of .int L1-6.
Exactly. Now this directive here is going to use up 4 bytes in the .text section, and the first byte of this particular construct will have the address of L1, or L1 has the address of that one single byte. In other words, L1 is an address of some memory location. Now, as an address, one way to look at it is, oh, it's an address, I can dereference it. But the other way to look at an address is, oh, it's just a 32-bit number, right? As a 32-bit number, I can add stuff to it, I can subtract stuff from it. It's just really just a number. So that means these 4 bytes here is going to contain a number, and that number turns out to be L1 plus 4. Okay, L1 itself is the address of something, L1 plus 4 is the address of something else. And same thing goes for this one. This is L1 minus 6. L1 itself is an address of a byte. L1 minus 6 is the address of 6 bytes before that particular byte. Are we doing okay so far? Yep.
Wouldn't L1 plus 4 be also the 0, 3, or 0x3, 0, 0, 0, 0?
It's a little Indian end of 4.
Okay, now your question is good because I have to remind you guys that there's no such thing as type in assembly language programming. So L1 plus 4 is literally L1 plus 4 bytes. So we are only counting in bytes when we do calculations, even when L1 seems to be indicating this is an address of a .int. Which reminds me to go back to here and this point here. A label is not a variable.
Okay.
It has no type information. So when we say plus 4, it literally means 4 locations, and each location is a byte.
Okay.
Okay. All right. So I'll let you guys get started with this homework assignment. And I think some people already have some clue as to how to get it started, because you have to work from the end result and then move your way backwards in this particular program. Okay. And also, even before you specify your code, okay, let me just switch back here. What you can do, one thing you can do is just to remember, what these were the locations where you have to specify something, and just stick something there so it won't complain, so it will at least assemble and link, and you can GDB it. Put a breakpoint right here, so that you're not even attempting to execute a single instruction, but instead of executing any instructions, you want to look at how memory is organized within this portion. Okay, particularly how is line 3 organized and how is line 6 organized. What exactly go into those 4 bytes on line 3 and those 4 bytes on line 6. That would be the first step that I do, the first thing to do. All right, any questions? No questions? The idea of this homework assignment is not to torture people. Some people may feel tortured, and I apologize for those, for that particular feeling. But the purpose of this assignment is really to make sure that people understand all the different addressing modes. Okay, because this requires a good understanding of all the different addressing modes in order to solve the mystery, in order to specify the 3 unknown pieces to get the result that we want. Okay, so that's the purpose of the homework assignment. Other than making sure people study and understand the addressing modes, this homework assignment serves no practical purpose. So there's the disclaimer. Okay, shall we move on? All right. I got one student in one of my other classes, who kind of commented on a homework assignment from somebody else, not from my classes, as somewhat pointless. But it's not the homework assignment that is well, the homework assignment may be pointless, but the purpose of the homework assignment is so that people understand the concepts that will be useful, actually at work. So that's why we have homework assignments that from time to time seem kind of pointless. We are now on to topic 3.
That was from someone else's class?
Yeah.
I know who it was.
From another college too, not even this college.
Oh, okay, never mind.
All right, so we are now getting back to adding numbers, but this time we're not going to talk about all the different rules of adding and subtracting in binary. This time we're actually talking about adding and subtracting as real instructions for the i386 processor. For the most part, this entire discussion also applies to just about any architecture out there. Okay, so if you generalize and just say, well, maybe it's not exactly the same kind of add instruction. Maybe we don't call the flags exactly the same way, but it's still pretty much the same principle. Okay, so we'll basically start with let me go back and see if I miss anything. Isn't that trivial? Adding is a fairly trivial operation for college students. One would hope. The purpose of this module is not to define adding, but to explain how it is done in a processor. The most tricky part of this entire module is how do we deal with signed versus unsigned numbers? And the answer to that question is awfully confusing, because it's simple. It is very simple. So by the time we get there, we'll talk about it. Okay, binary adding, we are revisiting the add rules, basically stuff that we have talked about already. So in this case, I also make something a little bit more general. Okay, let's go through these 4 rules first and see if there are any questions. In binary, 0 plus 0 is 0 with no carry. Does that make sense? 0 plus 1 is 1 with no carry. 1 plus 0 is 1 with no carry. And the only tricky case is 1 plus 1 in base 2 is a 0, but we also generate a carry of 1 to the next binary digit. Is that okay? All right. So this part is fairly easy to understand. So the next thing is I'm going to rewrite all of these rules here, all 4 rules, but using a slightly different notation. I use C as a function so that if you give me the 2 bits that you're adding, the C function will generate, okay, what is the carry to the next digit? Is that okay? And R is the result. If you give me 2 bits, I will tell you the result of adding those 2 bits in base 2. In other words, we are looking at exactly the same 4 rules as earlier, except the notation is different because I just use a function C to denote do we have a carry of 1 or do we have a carry of 0, and then I use R to specify the actual result of the carry, of the addition. Is that okay so far? That's good? Okay. So now the question is, can we implement something like this using just logic gates? That's the question. Can I have some sort of logic gate specification so that when the input is 0 and 0, the output is 0. When the input is 0 and a 1, the output is a 0. When the input is 1 and a 0, the output is a 0. When the input are both 1s, that's the only time the output is a 1. It's an AND gate, very good. Okay, conjunction in logic does that automatically. If you look at 0 as false and 1 as true, the AND gate alone can implement, the C function itself, the carry function. Is that making any sense? Okay. What about R, which is the result of the addition? There's no simple gate to deal with R. The easiest way to describe R is exclusive OR. How many people remember exclusive OR, or how many people took C where the exclusive OR operator was discussed? Okay, very few. Okay. Let's move on to the next slide because I think it is defined in the next slide. Now, the next slide talks about bit operators, and I'm hoping that most of us, understand the bit operators. Conjunction as a bit operator is just, it's also denoted as the multiplication symbol because that's basically what it does in logic. 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. The only time you have a 1 is 1 times 1. So that's why when you specify logic equations, a lot of times, we borrow the multiplication symbol from normal arithmetics to represent conjunction. Disjunction or a lot of times people use the plus, which can be confusing, okay? But basically you have 0 or 0 is 0, 1 or 0 is 1, 0 or 1 is 1, and then the last one is the only one that can be confusing. 1 or 1 is also 1. But when we write equations using logic, sometimes, a lot of times we use the plus symbol to indicate disjunction or the or. Negation, in logic, a lot of times, especially in computer engineering, it is used, people use an over bar to indicate the not or the negation of something. Okay. So that's just the bitwise operators. Now we can go back and talk about the carry function and also the result function. We talked about the carry function already. So basically, we can define the carry function as simply x and y. The multiplication operator is not even denoted here because in normal arithmetics, a lot of times when you say x times y, it is just written as xy. And it's the same way here. When we say xy in this case, x is a bit, y is a bit, we simply mean x, y in a conjunction. X and y in this case. Now, the result is denoted as x exclusive or y, and the exclusive or operator, a lot of times people use this plus symbol with a circle around it to indicate exclusive or. Exclusive or is not a very native type of operation, so sometimes, if you don't have the exclusive or operator or you want to specify in simpler operations, you can simply say Rxy is x y bar or x bar y. In other words, the first expression is a conjunction. It means x and not y, or not x and y. Okay, let's stop here for a moment. Are we sure that this is correct? When things get complicated, you cannot trust me. Let's go ahead and check whether that is right or not, and as a also do it as an exercise so that we can we can be sure that we know how to read that sort of notation. Okay, we have Boolean variable x, Boolean variable y, and then we have in this one I'm just going to spell it out using English words. So we have x and not y, and then this whole thing, or not x and y, like that. In other words, you want to look at this entire expression as a whole. How many combinations of x and y do we have?
3.
We have 2 variables, and each one is a binary. So how many combinations do we have?
4.
There are 4 possible combinations. X can be 0, y can be 0 at the same time. X can be 0, y can be 1 at that time. X can be 1, y can be 0. When x is 1, y can also be a 1. So those are the 4 possible combinations of x and y. Is that making any sense? Okay. All right. So let's figure out, what is the result of this entire expression when we have each of these combinations. When x and y are both zeros, what is this one? That's 0. That's 0, but that's a 1. 0 and 1 is a 0. So this entire side is a 0. And then on this side we have the same thing. Basically this is 0. This is 0. Oh, excuse me. 0, 1. This is 0. 1 and 0 is a 0. So this entire side is also a 0. 0 or 0 is 0. Very good. So we'll just go ahead and write down our answer. Okay, next one. Next one is x is 0, y is a 1. X is a 0, well, I'm just getting lazy because if you have a conjunction and one item is a 0 already, the whole thing has got to be a 0. So because of that, I can just say this entire side is a 0. We look at the other side. X is a 0, not x is a 1. Y in this case is a 1. 1 and 1 is 1. So we have 0 or 1, which is 1. Very good. And then we'll just work out the rest of it too. In this case, we have x being 1, y is 0, not y is 1. Then we have 1 and 1, which is a 1. If you have one side of an OR as a 1, you don't even have to bother with the other side because the whole expression has to be a 1 as well. So we put a 1 here. You guys know, that C uses a short circuit evaluation, right? Is that an explicit topic in the C class? Yes?
Yeah.
Okay, very good. Because that's a very, very important topic in C programming. Okay, the last one, we'll go ahead and just work this out entirely. X is 1, so this is a 1. Y is a 1, so not y is a 0. 1 and 0 is a 0. Well, we have a second chance of the disjunction being a 1, so let's go ahead and go for the second option. X is a 1, not x is a 0, so that means the entire conjunction has to be a 0 too. So now we have 0 or 0, which means the whole thing is a 0. Doesn't that do what we wanted to do? Okay, so that's why we can just say that R is x y bar plus x bar y. Okay, I specifically chose this notation instead of spelling out and, or, and not because people who have to deal with this typically have to deal with the logic specification like this. Any other questions? No other questions? The specification of logic like this goes just one level below what software people or programmers typically have to do. This kind of expression is used most often when people have to specify programmable logic gates or programmable logic in general. They come in different names because of the hardware differences. In the good old days, we have PALs. Programmable array logic, and then we have GALs. Okay, what is G? Nobody knows.
Genuine?
No, generic. No, it's something else. But it also implies it is programmable. And then we have CPLDs, and then we have FPLDs, and so on and so forth. Those are basically specific names for different types of hardware, so that your whatever device you are designing can have a programmable logic in it. In other words, you can swap out a chip or reprogram a chip in place in order to change the logic that that chip is doing. Okay. Next slide up. Now we talk about half adding and full adding. Now we're not quite done yet, okay? Because what we have just specified is the result of half adding. We're not really doing full adding yet. So now we have another notation to deal with. We will consider the addition of two binary numbers. X is a binary number, Y is a binary number. And we want to add these two into a sum, and the sum is denoted as S. Each one has n bits, so we're talking about a fixed width addition in binary. When we look at the entire number, the sum is x plus y. But we want to use a subscript to denote each individual bit of the addition. I was lazy, I did not want to draw a picture, but it is probably a good idea to draw a picture now. Let's talk about 4-bit addition. if I have 4-bit addition, I have x3, x2, x1, and x0 to represent the number x. I have y3, y2, y1, and y0 to represent the number y. And I want to add these two numbers together. Okay? Do you guys still remember your first homework assignment, the one where you have to convert numbers into binary and then do all the addition? So how would you call this location here using the notations that we have already? This would be the result of adding x0 and y0. So if I want to specify this location, this is r x0 comma y0. What about this one here? In our notation in this class, this represents the carry from the previous digit. But since x0, y0 are the least significant bits already, we know that there's no carry from the digit before because there's no digit before. Okay? What is this bit here? This is easy. Exactly. It's just the same result here. 0, y0, like that. What about this guy here? Well, this guy is a little bit tricky. So we'll basically talk about this, This one is easy. This one is a little more complicated. Okay? What is this guy here? It's C x0, y0. And there's no worry of these two making a carry because this is always a 0 here. So it cannot possibly generate a carry. I'm filtering. All right. What about this one here? That one is easy because this entire row is easy, right? This entire row is just a whole bunch of r's. So this one is really just r x1, y1. Okay?
So the bottom one is R inside the one?
Sorry?
Is it an R inside an R plus with the whatever the result on the bottom is?
Correct. So this entire row is like that. Okay, it's just the r of this one would be r x2, y2. This one would be r x3, y3. But this one is no longer as well. We just figure out this one, right? What about this guy here?
Is C of
Now
X
there are
and Y in the inside, X1, Y1, and then outside there's another C of
okay,
of that
very good.
result, and that,
There are two chances to make this a carry. Okay, what about this one? This one we know already.
It should be 0. You can't carry from the previous 0.
Oh yes, it can, because these two can generate a carry to go into here. So this one, I wrote this already here. It is x0, y0. Okay. What about this one here? There are two ways to generate a carry this time. The first way to generate a carry into this position is going to be C x1, y1. That's the first way to generate a carry into this spot. The second way to generate a carry to the same spot would be the addition of these two. So the other one is going to be C, and then this is R x1, y1, and then this one is C x0, y0. Okay? So now that we have figured out this one and this one, what goes here? An even longer expression, because the carry can come from two places. One is from adding these two together, and the second one is to add these two together. So what did I put here? We need an OR, because the carry can come from this source, or it can come from this source. So that's why it has to be a logical OR. So are we doing kind of okay with the notation? X, is a number. We chop it into bits. Y is a number. We chop it into bits. And then we have the sum at the bottom, which is what we want. But in order to get to the sum, we need to have all of these notations in order to do all the calculations. I think somewhere I have a picture. I remember vaguely that I drew a picture. Okay. So what this picture is representing is each block is called a half adder. Now what a half adder is basically what we have just talked about, so far. In other words, a half adder, which is a block. Okay, let me switch to a text editor here so I can just describe what a half adder is. A half adder has 2 inputs and 2 outputs. Okay? A and B are inputs. C is the carry as an output. And R is the result, which is also an output. Doesn't that kind of match up with what we have been doing, all along so far? And then when you look at this picture here, this is a 2-bit by 2-bit adder. It's adding 2 numbers, x and y. X is a 2-bit number represented by x0, x1. Y is a 2-bit number represented by y0, y1. And the sum are these 2 bits. The carries are represented internally. In other words, when you look at this gate here, which outputs K1, that's taking the carry of the adder, adding x0, y0, but it's also taking the carry from this part here. Now this time it is not really necessary because the input of B is always a 0, which means this carry is always going to be a 0. This little symbol here that looks like a moon kind of symbol, that's an OR gate in logic gate specification. So you can kind of imagine that if you have a 16-bit number adding to a 16-bit number, you basically have 16 columns of stuff like this, but they're organized exactly the same way as it is organized here. Are there any questions about this picture? Now, without really looking at all the details, okay? When I say details, I mean details. Okay? Without looking at the details like this, what is the significance of this discussion? We started off the discussion with arithmetic addition. Okay, 1 plus 1 is 1 with this 0 with a carry. We know how to add numbers. And we ended up with gate specifications in order to perform addition. Why is that important?
That's all computers.
Exactly, because inside the computer they're all logic gates. So you have to, at some point, translate whatever you want to do, addition, subtraction, multiplication, or whatever, you have to translate that into gate operations. And that's the real significance of this discussion here. Okay. Any questions at this point? Well, I have another question. Each box is called a half adder. Each column is called a full adder. In other words, we're adding 1 bit to a bit. And we can see that the carries of each half adder is ORed, and then it's fed into the B of the second half adder of the next digit. Okay? And we can keep this pattern going for as many columns as we want. If you want to add 64-bit number to a 64-bit number, we just end up with 64 columns, each one looking like this, and they all relate to the next column exactly the same way as it is specified here. But that particular way of organization has a problem. What do you think is the problem of this particular organization? Well, first of all, don't you think that this gate here, okay, I'm just going to show you with a pointer here. Don't you think this gate or this half adder really can't give you a correct answer until these two are done and the result of the carry is ORed? Then this guy can start to work. Does that make sense?
Yeah.
So that means these two have to be done. The OR gate has to settle down before the third column can start to work. The third column has to be done before the fourth column can start to work, and so on. This is called the rippling of the carry flag. So that means we need to, if you have a 64-bit adder, that means we have to wait for the propagational delay of 64 of these logic gate propagations. I don't think a Pentium can do calculations nearly as fast as it can now if that is how it is implemented. Okay, so this picture is really nice because it really shows us, how things can be organized in a very clean way. But inside a real processor, they don't do it like this. Okay, inside the real processor, they have a big mess of equations so that they can get to the end result as quickly as possible. Okay, what about the last carry? If you look at this picture here, you can just take this block here, copy and paste it as many times as you want. But in the end, the very last block will still have a carry coming out of it. So the question is that carry even important? The answer is yes, it is very important. Okay, the importance comes in many ways, but the first one is when we had 16-bit processors. Okay, that was a long time ago. But when we had 16-bit processors, do you think there was a need to do 32-bit add at that time? Sure we do. Or we did. Okay. Now that we have 64-bit processors, do you think there are occasions where we want to add 128-bit numbers? Sure we do. Okay. So why do you think that carry is actually important? Because it allows you to use multiple instructions to add numbers that are wider than your processor can handle in hardware. That's one importance of the carry flag. The other importance of the carry flag, not in the case of adding, is sometimes we look at the same flag as a borrow flag, okay, which is the flip side of adding. The borrow flag has even more significance, and we'll talk about that when we talk about subtraction and comparison. So we'll just keep in mind that the last carry is not lost. Okay, if you look at the previous picture, it looks like it's just going to La La Land, but it's not. The processor has a particular place to remember the last carry flag from the previous calculation. So it is remembered. And there's also a way to refer back to it. The processor can ask, hey, what was the state of the last carry in the previous calculation? Was it a 1 or was it a 0? The processor can ask that question, and depending on the answer, guess what? The processor can also choose to continue execution here, or I can choose to continue execution somewhere else. In other words, that's one way the processor can make a decision to determine which way to go. It's one of the most basic ways to do conditional, quote-unquote, conditional statements inside when we do assembly language programming. So the carry flag of the very last bit is very, very significant in many ways. Okay, we are running out of time, and we are currently, where are we? We are here in the last carry. And then the other thing, okay, this one I can cover real quickly. It doesn't show here. This is actually a Z. That's a Z. It just doesn't show. Maybe if I zoom in real big, yeah, that shows it. But the other stuff doesn't show very well. The PDF is better, for this purpose, because it just renders stuff a little bit better. But I want to show you what a Z flag is, or how do we know the result of an addition is all zeros. So I want to zoom in. Where's my zoom control?
On the bottom right. Mouse to the bottom right.
Bottom right.
Yeah.
No, it still doesn't show right. There should be an over bar, on top of the whole thing. Okay. Let's just talk about 4 bits. Okay. S3, S. I need a power tool to do that. All right. So if we look at a 4-bit and a 4-bit adder, the result is going to be 4 bits too. Okay. So what do I have to do to tell whether the sum itself is 0 or not? and I can only use logic gates. These are individual bits, okay? So one thing I can do is to say, well, let's take a look at the disjunction of all 4 bits, okay? Well, that's not going to give me a good answer, right? Because if any one of these bits is a non-zero, the disjunction itself is going to be a 1, okay? So that means if this expression is a 1, it tells me the answer, or the sum, is a non-zero. What if I put a bar on top of the whole thing? If I put a bar on top of the whole thing, that's a negation. So that means this entire expression will give me a 1 if and only if the result is 0. If you add 2 numbers and the summation, that the sum is a 0, this expression will be a 1 to confirm that it in fact is a 0. I know the logic looks or sounds backwards, but this is what we call a 0 flag or the Z flag. It's called different names. It's also called an E flag for equal, and among other things. But this is how the Z flag is defined. It is simply defined as the negation of the disjunction of all the bits after an operation. If Z is a 1, that means the previous calculation gave me a 0. If Z is 0, it tells me the previous calculation gave me a result that is non-zero. Okay? It doesn't sound like very useful to you, right? I mean, in the context of addition, it's not very useful. But in the context of comparison, it is very useful. Because now I can confirm whether 2 numbers are the same or not. Okay? Yep, go ahead.
But what if you have even ones?
Say again?
Even numbers of ones.
Even number of ones? It doesn't matter because this is just a disjunction.
But 1 plus 1 is going to be 0. And
No,
1.
this is not a plus. This is a disjunction. It's
okay,
OR.
okay.
So these are basically bitwise OR with all the different bits. Okay. So for now, 3.6 is where we ended. The next topic is also going to be important. That's a big, big, big question here. So you guys have to read it over the weekend so that we can talk about this next Tuesday. 2's complement. How do we represent negative numbers? That's the question.
You have test on next Thursday, right?
No, there will be no test till next Thursday because I always give you a practice test 1 week ahead of time. Since I have not given you any practice test yet, next week is safe.
Wow. 1 more way to survive.
And this just gives me more time to accumulate more material for the next test.